Good morning, good morning. Woo! My name is John Lambert. I've been doing security at Microsoft for 17 years. If I think about what got me into security, why am I still doing it? Well, when I started, they said, John, you'll be able to think evil, and people will pay you for that. I was like, this is awesome. Then I came to Microsoft, and they said, yeah, we'll pay you for it, but you need to do something about it, too. So that's been really fun as well. Another thing that has really kept me in security is that I feel like it's a field where you're constantly learning. You're learning about new threats, new attacks, new defenses. One of the things that I say, it's a little bit controversial, it's that offense and defense aren't peers, defense is offense's child. And what I mean when I say that is, defensive applications are done in the context of protecting from some set of threats, some set of attacks. It's always important to continue to understand the state of the art in attack in order to make sure you're doing what you need to do on defense. And BlueHat is a great conference that has a great mix of what's going on in attack, what's going on in defense. And I think the last thing about security that keeps me in it is the community. It is a field that just security gets in people's blood, and they just stay in it. And you get to know people, exchange ideas, and they change teams, and they change companies, but you see the same faces over and over again, and that's a really great thing. And I think that's one thing the security community in Israel really understands better than anybody else. But BlueHat from Microsoft is really an investment in that community. So by all means, get to know each other. If you catch me in the hallway after my talk, stop, say hi. I'd be glad to meet you. Last year, Mark Russinovich was on stage here, and he talked about how machine learning is being used in every corner of Microsoft. Every security product, every security team has embraced machine learning. I'm not here to give a machine learning talk, but what I wanted to come talk about was the systems that are being built today that incorporate machine learning and other techniques that are really operating on data. And whether you look at a lot of security startups or big companies alike, many organizations in them are building security controls, security solutions by doing an approach that's fundamentally harnessing the idea that you can improve security on data by using data to provide security. It's about mastering signals and data at massive scale, billions of events, and using that information in order to deliver security solutions. So I wanted to take you through a couple of examples here at the top to sort of bookend this. But then I want to kind of take you through what this blueprint of these systems look like and how they work. So to start, I'm going to go back 10 years in the past. How many of you, raise your hand if you've ever heard of MS-08-067? Okay, I figured in this crowd there should be a decent number. This was a very memorable vulnerability from Microsoft. It was a vulnerability that affected every version of Windows, was exploitable anonymously from any machine on the internet, and gave you code execution at local system writes. And when we found out about it, it was already being exploited in the wild, which, as an attacker, you go, this is an awesome vulnerability. As a defender, this just scares the willies out of you. If you want to hear any of the inside scoop about this vulnerability, the crisis manager for that case, and back in 2008 is Philip Meisner. Raise your hand, Philip. Go ask Philip, buy him a drink, ask him about this vulnerability. This vulnerability stands out in my mind because it's the only vulnerability I know that has its own t-shirt, coffee mug, throw pillow, I bought two, and not one but two cakes dedicated to it made by Red Team and pen testers. And they made these cakes for it because this was the vulnerability that kept on giving. They'd go into a client, and they'd like, all right, we're going to be here for a week. We need to pen test this network. And they're like, let's try MS-08-067 against the domain controller. Boom, machine wasn't patched. They own the network. Pen test is over. The reason I'm starting with this one is, my journey in learning how to get security signal from data really started with the telemetry systems at Microsoft. These are things that were built to operate on data at massive scale just to understand how are the products doing when we ship them in beta. Are they crashing a lot? Are they hanging? What's the user experience? And they didn't design them at all for security people, but we wanted to understand how could we get security signal from this system. And MS-08-067 was from many of the vulnerabilities that get reported to Microsoft because a customer who's being victimized contacts us or a security researcher has found it. This one was found deep in the crash telemetry, not in one of the noisy crash buckets of Windows error reporting, but in bucket number 45,000, way in the tail of data, and Microsoft had only gotten 2 crashes ever at the time that we found it. So that's one, and I'll go into more of that later. And you fast forward to the fall, there was a piece of malware called BadRabbit. It came around and, masquerading as an Adobe Flash update. You click that, you install it, and it starts overwriting your hard drive destructively. One interesting thing about this, when this malware strain came out, it was unknown to Windows Defender. It was new malware. And yet, Windows Defender started blocking this malware strain 14 minutes after it entered the world. And that's not because some steely-eyed malware researcher slid down from a pole and got busy on the keyboard real quick. It's because machine learning algorithms were sifting through gigabytes and terabytes of data and trying to understand what was new and what was a new threat out there, and it spotted this threat. And indeed, while eventually an antivirus signature was developed that was high precision, all of the blocks for the first wave of this attack were done without any human intervention at all by automated algorithms that were running and processing and sifting this data, blocking malware threats in real time. So you look at these 2 examples and you kind of think, what is going on with these kinds of systems where you're able to operate against massive scale and get signal out of them? And so that's why I want to talk to you today about how these things work. And I'd say they have really 4 major aspects. The first one, when people are designing a system that has data at the heart, customer activity is really at the center. And you can kind of think of the old approach was, you have a product, you put your IP in it, and that lets you protect a customer. This new approach that harnesses data, it's really your product plus your customers and the signals you get from them that gives you your IP. And so you think if you're going to buy one of these things, not only do you have to care about who made it, how good are they, are these people smart that made this product, but you also need to care about who the other customers are of the product, because it's the signals they get from those customers that fundamentally create the value and the protection. The second is that they are multidimensional. And what I mean by that is they're designed to process data both and make decisions about individual events, but also look at populations of events at a global scale, for example, to build a machine learning model to understand what is normal on a spectrum. They can look at data not only as it's happening, but trends over time, and that may be an important factor. And then they have sort of different levels of resolution that they can look at data. They can look at data at a very summary, coarse level, a hash of a file. Think a NetFlow record where you just have source, dest IP, source, dest port, versus very high dimensional data like a full packet capture, a sandbox run of a piece of malware. And these systems operate at all these levels simultaneously and are smart about routing what data they're looking at and sifting through the various layers. They are signal seeking. They both consume signals to find out what data they should be paying attention to, and they create signal. Like think you take a file, you run it through a sandbox, it generates all this activity. All of that activity is now signal for machine learning algorithms to use to build their models. And lastly, they are increasingly, because they're data-driven, they're being built in a way that moves them from a human-in-the-loop mode of operation, somebody has to respond to that thread and do something manually, to a human over-the-loop, where data is coming in, and the engineers are really making it so that they're controlling what data is coming in and what automated responses are happening, but that system is essentially running 24/7 without human intervention on the actual responses. And I would say part of the reason for the rise of these systems is they're especially empowered by SaaS and the cloud. SaaS is really vital here because all of this data and signal, if you think of a traditional on-prem software, all that data lives with the customer. You don't have it in a backend where you can do all this learning. But if your product is a SaaS app, like think Office 365, it's delivered to you through SaaS. Email flows through the service. All that data is already there within the service to build this. They have the data in order to do this kind of reasoning. And the cloud is there for the elasticity that's needed to do it at this high scale. If you look to the industry, you'll see a lot of players in the industry are bragging about the amount of data that they have. CrowdStrike here talking about they analyze 50 billion events a day. I talked to Alex Ionescu a week ago. He said it's up to 90 billion events a day. FireEye, you see them talking about 100 million plus graph database of all the knowledge that they have. So it's really the ability to harness and get insights from knowledge that the industry is moving to. So let me give you a little bit of an overview in the key aspects in these sort of telemetry-oriented security controls. So they have really 4 key aspects. The first one is they're designed to operate at high scale. Like I said, hundreds of millions or billions of events per day. To operate at that scale, you have to be able to make a lot of decisions very quickly without having to do a lot of analysis. And so you need to bucket the data that's coming into your into the product, into the control, in a very smart and intelligent way. And the whole importance of bucketing, and I'll give examples of it later, but the whole importance of it is so you can understand when you see something new, and you can benefit from knowledge you've already learned and apply it to the same similar threats that come across. The next thing is labeling, which is, of course, once you bucket stuff, then you can assign labels to it to say, we know this is good, bad, suspicious, whatever that may be. And once you can label things, you can decide to inspect it further. The next crucial aspect is what I call promotion signals. You need to know when you want to go deeper and analyze a particular input or file or network flow at a deeper level of analysis to get higher dimensional data out of it. You can't afford to do this on everything coming to the system, so you have to be smart about what you label and when you decide to promote it to do the next level of analysis. In general, the way this works is that signals come in from the raw events that come out, and as they get processed by these higher dimensional levels, the labels and verdicts and answers that they give propagate back up in the system. And crucial over all these layers is that they are self-tuning, cross-checking, and increasingly moving to a human over-the-loop. So those just sort of an overview of what the core aspects of these systems are, and I'll give you some specific examples here. So let's go back and look at Windows error reporting. So Windows error reporting. Anybody ever seen that dialogue before? Okay, so Windows error reporting operates at a huge scale. Billions of crashes come into it every single month. It needs to have an answer for those crashes so that if it knows there's a patch for that issue, go get this new video driver, it solves your problem. Those are its answers. Those are the labels and verdicts it needs to apply. At this first stage of bucketing, there's no PII collected at all. And actually, you'll see in this talk that a very smart approach to privacy is very vital for these systems to work well. If your system required all kinds of invasive data from people to work, well, one, you probably won't get it. And the data pump that fuels all those systems is just going to starve. And so it's actually a good approach to privacy is really important in order to build a scalable system here. So at this stage, there's no PII collected at all. And what comes into Windows error reporting when you click that button? Essentially, Windows error reporting builds a URL like you see at the bottom and sends that as a GET request to Microsoft. And what it's trying to do is understand effectively for an engineer what line of code crashed. Let's go understand that. That is the bucket that is trying to bin that crash into, so it can say this is a brand new crash we've never seen before, or this is a crash in that line of code that we've seen already. And if you want to decode what's in this URL, it's actually very straightforward. It's what app crashed, what version, when was that app compiled, what module crashed, version and timestamp of that module, what was the exception on that that was caused, in this case access violation, and then what was the offset, essentially what was the line of code within that module that it faulted at. And this very simple form of bucketing basically gets it down so you know every line of code that crashes and how many times it's crashing, and it lets engineers go and sort and say which crashes are driving the greatest amount of volume, go fix those first, go fix the next one second. And that's why every service pack, every release, every Redstone release in Windows, et cetera, they fix the top thousands of these buckets, they go pick them off and fix them. So if that's bucketing, as a security person that came into that, that really wasn't designed to get security insight straight off the bat. So what kind of security insight can we get? Well, if we look at this crash bucket, this is a crash for DNS.exe. And the important part is the exception code at the back. That C00409, that is the exception code for a stack buffer overrun. And so when we added the /GS flag to our compiler, if you compile code with it, it will recognize when a stack buffer overrun has happened, and it will it'll tear down the process, and it crashes with that particular exception code. So we don't know if this is an exploit for a vulnerability, but it could be a vulnerability there. And so that one is one worthy of further inspection. Here's another one. This one is the faulting app in this case is csrs.exe. Now in Windows, there's a system binary called csrss.exe. This is something trying to masquerade as it. You can see there's not even a legitimate file version there. It's blank. And so at least on the one hand, to a Windows engineer, he knows this is not a legitimate Windows binary. I don't have to look at, there's no bug for me to fix here. But from an anti-malware point of view, you say this is malware that is going around. Maybe we want to get a sample of that. This is an example of service host crashing NetAPI 32 at a particular offset, and we know that that line of code means somebody was trying to trigger that MS-08-067 vulnerability. And every time that hits, somebody in the world tried to exploit it, and it didn't work, and it crashed. If you want to study, you can learn a lot about attacks by studying exploits, studying failed exploits. What shell code do they use? What kind of techniques are they using? And that might be a crash bucket to watch closely to learn about every new technique. And then these next two examples are illustrating, that's quite an old version of Adobe Acrobat at the time, but it was an unpatched version, and this 0C, 0C pattern, that indicated a technique called Heap Spray was used. How many of you have heard of Heap Spray as an exploit technique? Popularized by Skyline, it was all the rage in 2006 to 2008, before data execute protection became very prevalent. And this told you that app, it had a vulnerability that was already patched, but this person didn't run a patched version on it, and it had crashed with the Heap Spray. And then we would see a bucket like this, Acrobat Reader with a full patch version at the time, all of a sudden crashed on a Heap Spray. And when we saw that, we knew a new exploit for a 0-day had just entered the wild. We didn't know what it was yet, but we knew that somebody was exploiting it, and we'd go after and go chase it. So if that's stage one, all we have are those like 7 parameters to go after. The next layer of Windows error reporting, stage 2, is where you actually prompt a user to collect a crash dump. What's in a crash dump? This is actually a visualization of a crash dump. If I put a bitmap header on a crash dump, and you put a picture, this is what you get. What's in that? You actually have a lot more data to work on that the debugger has access to. Loaded modules, crashing address, PEBs, TEBs, stack and heap memory. You got a lot more data to go, higher dimensional analysis that you can do. There's a debugger extension called Bing Analyze that Windows error reporting runs on all the crashes. And it benefits from, for example, every private debug symbol Microsoft has ever created. It has at its disposal to go match against those things. And it can do, instead of you having to deal with an offset, it can say, oh, that's the particular function that was in Microsoft Security Bulletin MS-07029, which was a vulnerability in the DNS RPC interface. And it makes it, you're able to bucket with a much better information at this higher dimensional level. Other clues you can get by processing this richer information. So this is an example of a call stack from Internet Explorer. I've highlighted 2 stack frames. The first one says, when IE crashed, it was parsing JavaScript. And that JavaScript, the last thing it had done was called the eval function. Now, a lot of exploit kits will obfuscate themselves, and then to decode their exploit, they will call eval on their obfuscated exploit. So if we got a crash with executing JavaScript during an eval, that already is a couple of clues that there's something more interesting in that particular IE crash. Here's another example from Word. This is a call stack in Word. When you're opening a file, that frame is on the call stack. And if you think about it, we're trying to sift through massive amounts of data to really pull out the ones that could be used in attacks. A scenario like user started Word, he had it booted for 10 minutes, went to Tools, Options, Proof, Autocorrect, Edit, and then it crashes. That's not interesting from a security point of view. That's not an attack scenario. You want to know when it crashes, when they're just opening the file, for instance. So these are the kind of signals that we can get when we have this higher level of information that's there. Here's another example. This is showing, visualizing a heap spray. The memory has been filled with NOP sleds. And if data execute protection is on for that process, that will fault with a depth violation, an access violation with those particular exception flags. And we actually changed Bang Analyze to recognize the address that it crashed at. Did it look like a NOP sled pattern to it? And if it did, it emitted a special problem class that gave us a clue that it crashed with a depth violation on a fill pattern that looks like a heap spray with a NOP sled. And that let us target those crashes much more carefully. And then another way that we would have the system find exploits is, or you could find exploits, is if this is what a normal crash looks like, just visualized as a bitmap. Think of that heap sprayed crash. The memory has been filled with NOP sleds of identical repeating patterns over and over, and megabytes of that. If you were to visualize a crash dump from something that had been heap sprayed, looks like that. And so now you can recognize exploits just by looking at what the crash dump looks like. And indeed, we got to the point where crash dumps come up in compressed. They're in cab files that compress them. If just by looking at the compression ratio of an IE crash, we could tell whether or not it had been heap sprayed. So lots of signals there. So if we go back to this, what made this what made this stand out to Windows error reporting? How were these layers working together to even bother to prompt the user to even upload a crash? Well, the first is it affected a fully patched version of service host. Windows error reporting is not interested in crashes for old buggy versions of apps that have potentially been fixed. If a crash happens on a fully patched version, that's a much more interesting bug to start looking to and prompting users for. The second is it had 2 hits. There's a lot of one-hit wonder crashes that happen once and we never see them again. Faulty hardware, buggy drivers, randomly flipping bits. Lots of issues that just never seem to reproduce. This one had 2 hits, so it had started to reproduce, and it had a security exception. So the system, without human intervention, had automatically gone in and marked that bucket to start prompting a user to upload a crash dump the next time somebody encountered it. Then, once that crash dump came in and got analyzed, it was able to go, and the analysis was able to determine automatically that where it faulted, you can see this service host, bang, import descriptor, etc. That was pointing off to memory that if you decoded that memory as if it was an instruction, it decoded to a jump ESP. And to an exploit writer, that is a control hijack. So that is a telltale clue that something interesting is going on there. The next is we had a lot of different detections for shellcode. We had, I think, a couple of 100 different recognized shellcode patterns, would emulate shellcode, things like that. And this noticed a shellcode pattern on the crashing stack. So when you have shellcode on the stack, you know you're getting warmer. The next is that another thread in the process was actually hijacked already and downloading a payload from a server in Japan. And the funny thing about this is, what it meant was the attacker had actually successfully used a zero-day, compromised that machine. It's downloading the payload from that slow freaking server in Japan. He gets impatient thinking it didn't work, hits enter again, and then crashes the process. And his or her impatience as a bad guy operator gave us this crucial clue that unlocked this vulnerability. And then the last aspect, of course, was that this NetAPI 32 has had vulnerabilities in RPC interfaces before. A very popular one that was being used by bots around the world was MS-06040. You can tell you work in security at Microsoft if you can just rattle off the bulletin numbers off the top of your head. This one was patched for that vulnerability. So now we knew we had a zero-day. Once we understood how to look and use Windows error reporting to find exploits, we said, I bet you we can learn a lot about finding zero days by just looking for exploits we already know about, vulnerabilities we already know about, and see if we can find people exploiting them. So this is all within a year. This was our first, this is back in 2007, 2008. This is us going and saying, we know these vulnerabilities were pretty interesting. I wonder if anybody exploited them. And this is like us filling out the chart of finding them in Windows error reporting traffic. And each one we found, we learned new shellcode, new hijacks, lots of things the attackers were doing to exploit these things. We would see exploits where the particular exploit writer used good error handling in their exploit. You know, a lot of exploit writers wouldn't bother to do that. They'd assume they'd get it right. We saw some that installed exception handlers and were very careful about what they were doing. We studied them in particular. So these are all exploits for Microsoft vulnerabilities. In some sense, you would expect to see people exploiting Microsoft vulnerabilities. What about third-party vulnerabilities? Remember, this is back in 2008. These were exploits that we found for third-party software that were being used in the wild. Many of these are ActiveX controls. You remember ActiveX controls went through a really bad run at that time where pretty much every ActiveX control had an integer overflow or a buffer overrun, and they were all being appropriated into exploit kits. And exploit kits, some of them had like 25 of them that they would say, well, let's see if any of these are on the machine. And here's some more. One of them, that Zango. Zango was a piece of spyware that had a vulnerability that somebody found, and then somebody else weaponized it to try to prey upon people that had that spyware that's on the machine. So no honor among thieves. And then lastly, these here were exploits we saw in the wild for software that's only used in China. And the rows that were yellow were the ones at the time we had found that we found them as 0-day. They were not patched by the vendor yet, and they were being exploited. And the number of pieces of software that were only used in China that were being exploited 0-day at the time was quite amazing. So that's the case in Windows error reporting, and I hope you got a sense of how important bucketing was to count things and recognize new, but also benefit from issues you'd already recognized, the signals that you can get from just minimal layers of bucketing to help you promote the right ones to get more data, and now you can do richer, higher dimensional analysis on that to get more signal, and that leads to some of the crucial breakthroughs. And then once you understand what that issue really is, we could go back to that stage 1 level of bucketing and say, yep, there's a solution for that, tell the person to go put this patch on, tell them to go to the NVIDIA website and get this thing, so on and so forth. Now I'm going to kind of go to the current time and give you another example from Office 365 ATP. So Office 365 ATP is a customer pays a few extra bucks per mailbox per month, and it takes every attachment that they get, and it runs it through a gamut. And the goal of Office 365 ATP, it reduces the impact from malware to a tenant to less than 1% compared if they didn't have Office ATP. And the first thing, the way this works is an ATP customer, like they'll receive a mail that's got an attachment. It first goes through a level 1 bucketing, which is, do we already know about this attachment or file? And that's using bucketing like, of course, if we know that hash is good or bad, we can process it immediately, and it gets actioned immediately. Office also, in the case of, if you think a malicious Office document that has a malicious macro in it, it's actually not the document contents that are interesting, it's the macro. And so they will compute a polymorphic hash of just the macro part, and they will bucket based on that. And so any wave, any campaign that comes in that at least has the same polymorphic hash as that are automatically bucketed as the same thing and get the same verdict. If it passes through that, it goes through a gamut of multiple anti-malware engines for diversity reasons. They use Windows Defender, of course, and they use a couple of others for diversity. Any verdicts determined at that stage are pushed back into these reputation lists. If it says it's clean, if all the anti-malware scanners say it's clean, it goes to what we call detonation, or running in a sandbox, where we spin up a couple of temporary virtual machines, have different OS versions, different versions of the application stack on there, and it interrogates it and tries to get as much behavior out of that application as possible. So you can see we went from just looking at the file at sort of a hash or polymorphic hash level to everything an anti-malware engine is going to do against it, including emulation, to running that file over detonation. And you can kind of think of maybe a 10 kilobyte Word document attachment is going to generate 10 megabytes of data and exhaust as it goes through this pipeline. All those verdicts are remembered and applied back. And then there's the last stage of trend-based detection, which is sometimes determining something malicious by itself is difficult, but you can see a quick pattern over time and know that that's a new incoming wave. And so even if, in the case of Office, even if at the time the mail is delivered, the system is not able to understand that individual sample was malicious, if because of a trend or pattern it realizes it's malicious within minutes, it automatically activates this feature of Office 365 ATP called time travel. And what that does is it takes it out of the user's inbox, it moves it into their spam folder if they've not opened it yet. So we've had cases of campaigns that we have our trend-based detection notice and monitor and find, and it takes that entire campaign and moves it to the spam folder even though it maybe missed all these earlier stages. And a crucial thing that with this example is how, in order to get to a more human over-the-loop system, you need the system constantly cross-checking itself and understanding the sources of gap and error in them. And so if you think about everything that detonation, sandbox analysis, finds is bad, that meant the anti-malware scanners missed it. And so all of those true positives are fed back as verdicts and feedback to our anti-malware engine to go improve its verdicts. Windows Defender uses machine learning algorithms in itself, and they're able to go consume those signals, those verdicts, automatically. And the next is, of course, if detonation found the file, believed it was good, and it's later found to be bad, that's a signal we need to improve the detonation process. And one thing that we do is a new threat may be unknown to anti-malware on day 1, but by day 2 or day 3 or day 4, they have anti-malware signatures. And in general, if an anti-malware signature is ever going to get created for that threat, it happens within 3 or 4 days. And so you can go back retrospectively and run updated SIGs against previous inputs, and that's a good way to find things that got past your detonation. And those feed back as labels on that missed data, and we have machine learning models that are consuming those labels, those better verdicts, and improving the output of the detonation labeling and classification. So it's important not just to have the layers to help you scale, but also this cross-check so you get these signals going back up and down the system so it can self-correct over time. And I mentioned in the beginning, this is for Office 365 ATP customers. So that's the data, that's the signal that's coming into the system. If you want to make it better, you're going to go seek out more signal. We can take, and if we see a funny pattern with email, we will detonate attachments and run it through this full pipeline, even for non-ATP customers in some case, because we see what looks like the beginning of a campaign. And if we find it's bad, we will block that file for that customer, even though they're not paying for Office 365 ATP. Outlook Premium, Outlook. So there's a lot of sources of data that we can use to go improve this system. And essentially, you want to go get the most diverse, the freshest amount of data as you can. And when you build these data-driven systems, one way to think about it is, who in a product team is the most excited when you get new customers? Usually it's the sales team. The sales team is the most excited when you get new customers. But if your system, if the key to its effectiveness is based on data from customers, in these systems, it's the engineering team that's super excited when you get a new diverse customer in a new geo or a new segment or a large seat customer that's going to have a big attack surface and going to see a lot of richness from a threat point of view. And then the last example here is the one I mentioned about BadRabbit with Windows Defender. And so Windows Defender, of course, runs a classic anti-malware load on an endpoint, but it actually also has local machine learning models that are there designed to run on unknown threats. And the goal of all of that is to be able to provide an answer within a millisecond. If it can get an answer within a couple of milliseconds, it can block the file. All that happens on the client. If there's some clue that that file is potentially malicious, but it doesn't know for sure, it can start to send increasingly progressive amounts of metadata to the server, to the cloud, and there are machine learning models that will operate on that metadata in the cloud to make a snap decision. If those algorithms think it's even more suspicious, but we're not conclusive about it, it can prompt the user to upload a sample. A sample can come through. Now they have the full file to analyze. They can send it to a detonation sandbox. Now they get much more rich data out of that. They have ML models that run on the output of full static analysis plus full behavior analysis. And then with this accumulated data, they can look at it on not just a sample basis, but a global basis and build models over that. So if we combine these and take this back to BadRabbit, what was going on here? So with BadRabbit, patient 0 encountered the first instance of BadRabbit. It was flagged as suspicious by the Defender engine because the file was not validly signed. It came down from the browser. It was an executable. And that meant it tripped a certain ML model of suspiciousness that went up to the cloud. And then it requested a sample, and the sample came up. And then another ML model ran just on metadata, the 1,000 features of metadata that it picked out of the sample, hashing different parts of it, looking at all the imports and code blocks and so forth, looking at it from all these different dimensions. And even that was strongly suggestive that it was malicious, but not fully conclusive with just static analysis. So in that case, the result was inconclusive, but it was suspicious enough that it queued it for sandbox detonation. That process ran 90 seconds later. It got its answers. Machine learning models ran on the output of behavioral information from sandbox detonation plus all the static features, and now just understood that that was indeed malware and was providing this block verdict. And so while patient 0 sort of got the malware delivered to them, all those verdicts on that were then able to be applied to any subsequent patient that got the malware after that and was blocked in real time, all by this knowledge that was learned on the cloud without a new DAT file update going down and what have you. And this is, I think, a good example of humans were not involved in any actioning of this process at all. This was a loop that was designed and engineered to do this progressive analysis, send these signals up, push these labels back down in order to provide protection within minutes. So I just have a few kind of closing remarks on this. Anytime you build a massive system at scale like that, you not only have to engineer it to get the results, but you have to be very resilient for it getting bogus or bad data in there. You'll occasionally get verdicts from anti-malware that are just wrong. They're false positives. And if that goes into your machine learning model, you're going to learn on the wrong things. You also have to threat model this system against attacks where attackers may try to poison information at various layers. And like I mentioned earlier, privacy is very important in these systems because you're collecting data fundamentally in order to do it. And you need that data pump working for the system to work well. And so a well-tailored approach to privacy is your friend to make a system like this effective. At Microsoft, we have regional data centers where the data never leaves a law enforcement jurisdiction. That's important to some customers. We have progressive collection, notice and consent, opt-in, opt-out, so on and so forth in order to do that. And then I would say, if you're a defender, how can you use a system like this? Think about what signals you can integrate it that only you know as a defender from your network. What your users are up to, what certain data or users mean, and things like that. So with that, I hope you got a sense of this new pattern of security control that's being developed that really has data at the heart of it, and it's about mastering the signals that you can get from data, but building it and designing it in a way that lets you scale to billions of events per day, but allows you to get the richness and analysis you need to get the quick eye on the top threats that are there. So with that, thank you for your time and enjoy the conference.